In this first part of the video, I'm going to show you what you'll see on an oscilloscope. Now, an oscilloscope shows you a graph of amplitude of voltage against time. You can get probes which convert current into voltage, but the oscilloscope is still showing voltage. So that is basically what I'm going to show you on here. So as time goes on, it shows you what the amplitude of the voltage was at that moment in time, which is why it sort of moves across. If you set the time base slow enough, you can actually see the signal being generated across the screen. Now, what I'm showing here is supposed to be a sine wave. So this time across the horizontal axis is showing quite a short time, and if we imagine that this is a 1 kilohertz signal, this section of the screen is showing 1,000th of a second, and then this section is showing the next part, and by the end of the screen it should just about have got back to the top. So it's showing 2 1,000ths of a second. This is very useful because it allows you to see what's actually happening on a wire or at a location in, say, an amplifier. So you might be injecting a 1 kilohertz tone into the amplifier, and you might want to see what happens to that tone as it goes through the amplifier. So the primary use of an amplifier is to make it louder. So without any tone adjustments, without any effects or anything like that, all you're looking for is for the amplitude to increase. So as the signal goes in, and the signal might be 0.5 volt, so this here might be 0.5 volts. When that comes out of the speaker terminals on the back of the amplifier, that could be 20 volts, 25 volts. So obviously the amplifier has done its task. The reason that we want to watch the signal as it goes through is because there may be faults within the amplifier. So for example, there's no sound coming out of the amplifier. You can inject a 1 kilohertz tone into the input. You can then, with the end of the oscilloscope probe, you can touch the pin of the preamp tube where it comes in and see that the signal is reaching the tube. You can then check the output of that tube and see that it's been increased in volume. You can then follow that through the tone stack, and eventually you can find where the signal disappears. That gives you an idea of where the fault might lie. It also might show you interference, and it might show you other issues. If, for example, you look at the signal on the output and you're getting something like that where it's uneven, that might point to a particular part of the amplifier, such as the phase inverter. Here the signal's clipping on just one of the one side of the wave. So this is why, as a builder of amplifiers or a repair of amplifiers, you might want to use an oscilloscope. Next, we're going to look at a spectrum analyzer. Now, the oscilloscope showed you a graph of amplitude against time. With a spectrum analyzer, it shows you a graph of amplitude against frequency. So imagine that we have 10,000 hertz, 10k across the graph, and we're injecting that 1 kilohertz tone that we showed on the oscilloscope. If we look at that on the spectrum analyzer, imagine that this is a tenth, this is another tenth, another 5. Right, so there, each one of those is 1k, and we're injecting a signal of 1 kilohertz. What you'll see here, a perfect 1 kilohertz tone should just be a spike here, but that's not likely to happen. So what you're more likely to get is something such as that. So the same signal, the 1 kilohertz tone, is now appearing as a spike. Now, this is less useful whilst building amplifiers than being able to see the tone. The signal as a sine wave, for instance, because imagine if there's some interference and it's affecting the signal. This is still going to show as a spike here, unless the interference or the signal is altering the frequency. So you're just going to see a spike. So in reality, this is the reason why amplifier builders, repairers and hobbyists tend to buy an oscilloscope rather than a spectrum analyzer. But there are things that a spectrum analyzer can do, or is better at, than an oscilloscope. So we're getting a signal, just one simple thing. We might have a hum. Now I'm going to change this now, and we're looking at the signal now, 1k. So I'll get rid of our input, and this is now 1k left to right, and we're inputting a 600 hertz signal, but we're getting some hum, and we don't know whether the hum is 150 or 120 or 60, depending on your mains. And that would allow us, by knowing that, to see whereabouts in the circuit that hum is being created. Now, if we can see a spike there at 120, we know that it's that the spike is at 120, and that can basically show us where in the system, in the power supply, the fault occurred. If the signal was at 60 or 50, then that would allow us to know that the hum is getting into the system at a slightly different location. If it's straight mains hum, you're looking at 50 or 60. If the hum is being induced later on, after the signal's been rectified, then it would be 100 or 120. So that would allow you to know whereabouts that's happening. That's just one thing. Another thing would be to look at the frequency response. So if you put in white noise, for instance, and you're getting a signal such as that, that would show that the response is quite linear all the way across. But if it's doing this, you know that it's cutting off at about 650, and that might show you where a fault is occurring. Another thing would be harmonics. So we have a signal coming in, and we're getting spikes either side of the main signal. These are harmonics, and again, that might lead you to knowing what the fault is or where to look. This video isn't going to be about what to then do with it. It's simply to demonstrate the differences between these devices. Finally, a multimeter. Now, a multimeter is usually the first piece of electronic test equipment that anyone gets. And to compare a multimeter with an oscilloscope, for instance, we have time and amplitude. A multimeter is basically giving you the amplitude at any single individual time, and you're watching it there. So that dot there, that would be the reading from the multimeter. So it's effectively just giving you the amplitude at the time. There's no graph showing you how that amplitude's changing. If it's changing quite a lot, you'll just end up with a display that is changing rapidly. You can, if you have an AC and DC switch on the multimeter, you can see by changing it from AC to DC, if you have a repeating value, if it's static. Looking on a multimeter, a DC signal would be like that, whereas an AC would be like that or similar. A multimeter is just going to give you the spot at that time. If you're looking at an AC, then it's going to be going up and down, up and down, up and down, up and down. If it's too fast for the display to change, you're just going to get a reading which is somewhere in the middle, but not very useful. The AC function will try and give you the average. The RMS is root mean squared, which means that effectively by squaring something you're getting rid of the negatives, and then you're finding the average of those. So that would be the RMS value. If you've got an AC reading on your multimeter, that's what you're looking for, that line there. So the only repetitive thing that the multimeter can realistically do is show you the difference between DC and AC. There are some multimeters which have logging functions or graphing functions. Well, effectively they're doing the job of an oscilloscope, albeit simplistically. Next I'm going to show you the actual devices themselves. So here we have a selection of multimeters. These are just the basic multimeters that most people start with. There are also desktop multimeters, such as my Keithley, or slightly older Philips Fluke PM2525. But basically these do the same function, and most people prefer the handheld ones, at least to start with. Moving on from that, oscilloscopes. This device here is a Tektronix 2225, which is a very nice oscilloscope for audio work. It's 50 megahertz. It's more than adequate for anything that you're likely to do with an amplifier, and a fantastic scope to start with. After that, most people will then move on to digital scopes, and my scope at the moment is a Siglent SDS1104X-E, and prior to that I had Unity UTD 4102C. So these are the types of scope you're likely to come across. If you saw my previous video, you'll see my latest acquisition, which is the 3582A Hewlett-Packard Spectra Analyzer for audio work, and my other Spectra Analyzer is a tiny Spectra Analyzer. These are very cheap. You can find these on eBay or Amazon, AliExpress and the like. These are not very much use for straight analog work. They don't start low enough, and they're more for other tasks. Finally, a signal generator, which I'm going to be using to show you the differences. This is an FY3200S, a digital arbitrary waveform generator, and going back, an analog equivalent is the Leader LAG-27, which is an audio signal generator, and quite a nice device to use. So for this demonstration, I'm going to be using a 1 kilohertz signal from the signal generator, and that is being fed into all three of the multimeter, the oscilloscope, the multimeter, and the Spectra Analyzer. So going to the oscilloscope first, we can see that the signal is being fed into the 4th channel. So I can get rid of the other channels, and we have the signal. You can move the signal up and down on the display using the vertical position, and this is our sine wave signal. I can zoom in, I can make that larger, sorry. Now that's showing us 100 millivolts per square, and we can see the display. It's moving around a little bit because the trigger point is quite close to the level. By trigger point, obviously if you're watching a signal that is moving, you need to know, the device needs to know where you want to start looking at that, and you use the trigger control to set the point at which you start displaying the wave. If people are interested, I can do a video specifically about how to set up and use an oscilloscope, but this is more for comparison purposes. So that is a 1 kilohertz signal on an oscilloscope. If we now move to the Spectra Analyzer, and you can see on here, this is 1000 hertz or 1 kilohertz, and we have a spike. There's a function you'll find on the Spectra Analyzer, and it's this here, this position control. And what I can do is I can move this dot at the bottom, and it follows the signal. So as it reaches 1000 hertz, it jumps to the top of the signal, and by reading where the marker is, you can see the frequency of that particular point. If we go back this way, that's showing the 0 point, and there seems to be a small a small signal at 400 hertz. Not really sure what that is. It may well be caused by the fact that I have all three devices connected together, but it is quite a small mark. And then we move over to the the multimeter, and here we are showing the voltage as an AC. So that is the AC reading. If I switch to DC, it's basically averaging it out and effectively a negligible reading. That's flicking all the way around about 0. So it's showing that basically there is no DC. We'll go back to AC, and we have the RMS value of that signal that's being fed into the other two devices. So you can see that by using the multimeter, you can actually tell that you have an alternating value, because by switching between DC and AC, you can see that it virtually disappears on DC. On AC, you've got a reading which is quite steady, so you know you have a good repeating pattern, but you don't know what that pattern necessarily is. It could be a larger amplitude and a slower or faster amount. It's the average, so basically that's all you're getting. Obviously with the oscilloscope you can see it, and with the Spectra Analyzer you just know the point where that's at. If we change the setting on the signal generator to a different kind of wave, and we'll go with we'll go with a square wave. Okay, so we now have square wave. So looking at that on the oscilloscope, you can see that you can just see the top bits, where it changes from the top part to the bottom part is virtually, you virtually can't see it. I can see it on the screen. If I move out a bit, it's making little difference. If we go back to the multimeter, you can see that the AC voltage has actually changed. This is because the root mean square of a square wave is different from that of a sine wave. So you can see that the AC voltage has increased slightly. And if we then move to the Spectrum Analyzer. We're still getting the same 1 kilohertz signal.
Thanks for watching. The video was designed to show beginners the difference between the three devices, and to show that we might use different devices for looking at waveforms and values in different ways. If people would like more in-depth videos on using the Spectra Analyzer or an oscilloscope or even a multimeter, just let me know in the comments, and I'll do a video specifically about each device. Thanks a lot for watching.